Sorting is the process of rearranging items so that they are in order. Personnel records may be sorted alphabetically or by social insurance number. Hockey players may be ordered by lifetime goals scored. This film presents and compares 9 different sorting techniques, or algorithms: 3 insertion sorts, 3 exchange sorts, and 3 selection sorts. Our first 3 techniques are called insertion sorts. Each one works by inserting new items into data that is already in order. The simplest insertion sort is called linear insertion. The linear insertion sort compares the first 2 items to see which is smaller and discovers that they are already in order. The third item is larger than the second and in its correct position relative to the other 2. The fourth item is not. Thus we find the correct position and insert it into place. With each new item, we look for the correct position, move the intervening items out of the way, and insert it. Here an item is already in the correct position. If there are n items, we make n-1 passes over the data, each with order n comparisons and movements. Thus linear insertion is an n-squared sort. Now let's try this again with more data. In deciding where to insert the item, we examine each consecutive location, looking for the correct position with a linear search. As you can see, this is very time-consuming. We can do better by using a binary search, yielding the technique known as binary insertion. Binary insertion first divides the search interval into 2 and discards half of it. Again, we divide the interval in 2 to further narrow the search. We divide again with a third probe, discover the correct position with the fourth probe, and insert the item. We begin again, discarding half of the search interval, and half of the remainder, and again half, to find the position in the fourth probe. Thus the number of comparisons is usually reduced, although not always, since here linear insertion would have been faster. The binary search reduces the comparisons to order n log n, but we still need order n squared data movements. To reduce the number of movements, we use a method invented by Shell. The shell sort, instead of considering all items at once, sorts small groups of items. We start with groups spaced widely apart, in this case, every 5th item. We do a linear insertion on the first group, and on the second, and on each subsequent group. Notice that each movement takes an item 5 positions towards its ultimate destination instead of only 1 position. Next, we operate on groups spaced more closely together, in this case every third item. Again, we perform linear insertions on these groups. The final pass is also a linear insertion sort. It goes quickly because the data is already almost sorted. But it is not obvious that the shell sort is faster than the other two methods, and if it is faster, how much faster? So let us run some experiments and see. Consider the three techniques on n randomly selected data items, where n ranges from 10 to 500. First, consider the number of times we compare two items to decide which is smaller. The number of comparisons for linear insertion grows as n squared. For binary insertion, as n log n. For the shell sort, approximately the same as n log n. How about the number of times items are moved to get them into their correct positions? In linear insertion, the number of movements grows as n squared. Binary insertion makes the identical movements. The shell sort, however, yields a significant improvement. Total computation time is a function of both comparisons and movements. We have coded the algorithms as similarly as possible in the C language on a PDP 1145 computer. Linear insertion is clearly order n squared. Binary insertion yields a slight improvement. The shell sort yields a significant improvement. Another way of visualizing this is to imagine three identical machines using these three techniques to sort identical sequences of 250 items. See if you can identify which machine is using which technique. Keep your eye on the bottom machine at the beginning. Our next three techniques are called exchange sorts. Each one works by exchanging pairs of items until all items are in order. The simplest exchange sort is called the bubble sort, a method whose fame exceeds its virtues. We begin by scanning up the data, exchanging adjacent pairs of items where necessary to move the smallest item to the top. We scan the remaining items, performing more exchanges. Now the second smallest item is in position. Each successive pass guarantees that one more element is in its correct position. There are n-1 passes with order n comparisons and movements in each pass. Thus, the bubble sort is an n-squared sort. The data is now sorted, but the program does not discover this and continues through the remaining passes. To speed up the bubble sort, we must notice when items are already in order. One method that does this is known as the shaker sort. The shaker sort, just like the bubble sort, first moves the smallest item to the top. Now we reverse directions, start at the top and move the largest item to the bottom. We alternate forward and backward passes like a cocktail shaker. Notice that the 4 items about to be considered are in the correct order. The shaker sort will discover this because from here up it will swap no items. Thus they must be in the correct order and also in their correct position. The shaker sort is better than the bubble sort because it transports large as well as small items towards their ultimate destination and because it takes advantage of order in the data. But even better is the best of the exchange sorts, the quick sort invented by Hoare. The quicksort begins by choosing one item as a pivot. It will rearrange the sequence to separate all items smaller than the pivot from all those larger. We scan down from the top looking for an element larger than the pivot, and scan up from the bottom looking for one smaller than the pivot, and interchange the 2 items. We again look for a larger item and a smaller item, and interchange them. We continue this process until the smaller items are separated from the larger items. Then move the pivot between the 2 sets. Notice that everything above the pivot is smaller than everything below it, thus we need consider the pivot no further, and can apply the technique recursively to the 2 sets. With a set of smaller items, we choose a new pivot, find a larger item, and a smaller item, and interchange them. Again, a larger item, and a smaller item, and a swap. Now we move this pivot between the 2 sets of items into its correct position. When we have 4 or fewer items to sort, we use a simpler technique such as the bubble sort, not shown here. Now we begin again on the set of items larger than the original pivot. How much better is the quick sort than the bubble sort and the shaker sort? We again resort to experiment. The number of data movements for the shaker sort is identical to those of the bubble sort because the exact same exchanges are done, albeit in a different order. Again, let's race the 3 machines in a typical sequence. One will use the bubble sort, one the shaker sort, and one the quick sort. Can you tell which is which? So that you don't fall asleep, we'll now speed up the race by a factor of 5. Our last 3 techniques are called selection sorts. Each one works by successively selecting the smallest item, then moving it into place. The simplest selection sort is called straight selection. The straight selection sort scans through the data looking for the smallest item. And moves it into the correct position. We then look through the remaining data for the next smallest item. And move it into position. Notice how this differs from an insertion sort. In an insertion sort, we find the correct position for the next item we are inserting. In a selection sort, we search through the entire sequence for the smallest remaining item. Each of the n-1 passes takes order n comparisons and a single data movement, so straight selection is an n-squared sort. To speed up the selection sort, we organize the data into a tree and apply a technique known as tree selection. Tree selection first compares pairs of items at the bottom level, selects the smaller of each pair, and promotes it to the next level. We now compare 2 items that have been promoted and select the smaller of the pair. This leaves a vacancy in the tree, which we immediately fill. We compare another pair of items, promote the smaller of this pair, and fill the vacancy that results. At last we reach the top of the tree. Fill the vacancy at the level below, and the next vacancy, and output the smallest item. We can now select the second smallest item, fill the resulting vacancies, and output it. Each successive pass outputs the smallest remaining item. Since vacancies always result in immediate promotions, Knuth has labeled this the Peter principle sort. Because each pass examines only one branch of the tree, tree selection is an n log n sort, but it uses 3 times as much storage as straight selection, space for the original input data, for the body of the tree, and for the output data. To achieve the same efficiency without the extra storage, we use the heap sort invented by Williams. We organize the sequence into a tree in which the first item, the 3, is at the top, and the last item, the 4, is at the bottom right. The first pass of the heap sort will move the largest item, the 7, to where the 4 now is. This will happen in 2 steps. The first step will rearrange the tree into a special kind of tree known as a heap, in which every item is larger than all items in any subtree below it. Thus the 7 will be at the top of the tree. The second step will be to move the 7 to the bottom right of the tree, to the end of the sequence. We first make the right subtree into a heap by moving its largest item to the top. We make the left subtree into a heap by moving its largest item to the top. To make the entire tree into a heap, we make the top subtree into a heap, and then fix up the left subtree to again make it into a heap. Since the largest item is now at the top of the tree, we can move it from there into its correct position at the end of the sequence, where we need consider it no further. Note that the remaining tree is no longer a heap, but only because of the top item. So we must begin at the top, rearranging so that the second largest item, the 6, will come to the top, and so that the entire tree is again made into a heap. We now move the 6 into its correct position, and also remove it from the tree. Each successive pass brings the largest remaining item to the top of the tree, and then switches it into its correct position. Again, let's resort to experiment to evaluate the algorithms. Notice that straight selection by its very nature requires very few data movements, since most of the work is done in the comparisons. And here we go again, with straight selection at the top, tree selection in the lower left, and heap sort in the lower right. If you're getting bored, let this be a lesson about n-squared sorts. To conclude, We observe all 9 algorithms, each with 2,500 identical data items. So that everything will fit, we represent each item with a dot, its position by its horizontal coordinate, its value by its vertical coordinate. Thus, unsorted data appears as a cloud, sorted data as a diagonal line. We won't show you the whole race, because it would take another 54 minutes for the bubble sort to finish. Instead, why not see the whole film again?